So we're on page 5 of the Unit 6 project, From Physics to Chemistry. And I want to remind you of our big ideas here at the top of the page. Elements can be identified by the light they release. Different elements release different kinds of light, as we saw with the flame test. And you also read about it in the auroras and watched videos about it. Basically, the idea is this. Here's an atom. The nucleus of an atom is surrounded by electrons that orbit around it, huh? Everybody look up here. Act this out with me, in fact. Here's the nucleus of the atom. Here's electrons orbiting it. Now, when something excites that atom, this is one of my favorite science words, because it doesn't seem like a science word, does it? But this is the official name for it. Keep orbiting. Electron orbiting the nucleus. When it gets excited, now the electron's way out here. It has more energy, doesn't it? But it can't keep that energy forever, so eventually it calms down again. And when it calms down is when it releases the energy as light. And that's what happened when we did the flame test. The heat from the flame excited that atom. It also happens with an aurora. The magnetic field interacting with the solar wind excites the atoms. So what do? Their electrons go from here to out here, and they're all excited, but they can't stay there forever. So they fall back down. They get closer to the nucleus again. They relax, and they release light when they're giving that energy away. So we're going to see that over and over again, this whole process of gaining energy and then releasing it. In fact, why don't we go to the bottom of page 4, and I don't know if you read this yourself or not, but why don't we go ahead and read this together about St. Elmo's fire. And you can highlight the important stuff as I read it to you, okay? So St. Elmo's fire has to do with sailing ships back in the old days, although it still happens today out on the ocean. And look closely at that image of that sailing vessel. Do you see the lights coming off the tip of every mast and beam? See that? That's St. Elmo's fire. It starts to glow because the atoms are excited and they release that energy in the form of light. So highlight the important stuff. Here we go. St. Elmo's fire is a weather phenomenon in which luminous plasma, in other words, glowing, luminous, plasma is a very hot gas. St. Elmo's fire is a weather phenomenon in which luminous plasma is created by a corona discharge from a sharp or pointed object in a strong electric field in the atmosphere, such as those generated by thunderstorms or created by a volcanic eruption. So that's why we see this little, they're not really flames, but it's glowing light at the tips of the mast. The top of that wood pole is the mast, right, that holds up the sail of the ship. And we can see it also on the cross beams that hold the sails out side to side. It's because it comes off of a sharp or pointed object. They call it a corona discharge. Corona is crown, right? It comes from the Latin word for crown, and I think it's still the same word in Spanish, isn't it? And we're well familiar with that word today because of the coronavirus, which is surrounded by these little spikes that make it look like a crown. But we use that word other times too, like there's a layer of the sun on the very outside that they call the corona. You can only see it during an eclipse. So it's amazing. You should go see an eclipse if you get a chance. I don't know, maybe you saw the one here a couple of years ago. It depends on where you are. There's an eclipse every couple of years somewhere on the planet, but a lot of them, of course, since the planet's 3/4 covered with water, 3/4 of the eclipses are only seen from the ocean, huh? So a lot of them we can't see. At any rate, we get this electrical discharge during a thunderstorm coming off the tips of these sharp objects, especially out at sea, and they named it after St. Elmo. It may be seen as a blue haze around persons or objects during a thunderstorm when it can be a sign of an imminent lightning strike. So if you're out on the top of the mountain and your friend starts to glow blue, you probably need to get to shelter, huh? Of course, most likely the first thing that's going to happen is your hair starts to stand up. It's crazy. If that happens when you're outside, you need to get someplace that you're not going to get hit by lightning. That might mean underneath other trees because they're taller than you. The lightning is more likely to hit them than it is you. So get to shelter if that happens. St. Elmo's fire is a bright blue or violet glow, appearing like fire in some circumstances, coming off of tall, sharply pointed structures such as masts, spires, and chimneys, and on aircraft wings or nose cones. St. Elmo's fire can also appear on leaves and grass, and even at the tips of cattle horns. Imagine that glowing blue-purple light coming off of a cow's horns. Yes, sir. The nose cone is the front part of an airplane. So, like, let me see how well I can draw an airplane here. Here's the wing coming back. Is that okay? Another wing. This is the nose cone right there. Often accompanying the glow is a distinct hissing or buzzing sound. The nitrogen and oxygen in the Earth's atmosphere cause St. Elmo's fire to fluoresce with blue or violet light. Again, elements give off different colors when they're excited, huh? And moving on to this big question, how can I analyze spectroscopic data? It depends on the color of light given off by the atom. By looking at the color of light given off by that element, that's the spectroscopic data we're talking about, is the colors that it releases. We can then figure out what that material is made of. Does that make sense? Have you ever heard that they've said, oh, a new planet was found and its atmosphere contains nitrogen? Have you ever heard something like that before? Well, I hear about that stuff when I read the science news. How do they know it contains nitrogen when it's so far away? It's because we can use this spectroscopic data to figure it out. And we're going to practice exactly that today. So our first activity today is called Spectral Fingerprints. And it looks like we want more highlighting here, huh? As shown with the flame test, different materials emit different colors of light when they gain and then lose energy. Before moving on to our spectral analysis, let's clarify some vocab. So, in fact, I want to back up a minute. Who knows what that word emit means up on the top line? What is emit? Yeah. To give off, to release, right? To emit something is to give that thing off, to release it, to send it out into the world. Okay? So different elements emit different colors of light. First, they gain energy, like from the heat of a flame or from an electrical phenomenon. And then they lose that energy, and in the process of losing it is when they emit the light. So, let's see. Are you guys good with this word spectrum? We've been using it, and we use it for a lot of things. A spectrum is a range of objects where one thing kind of flows into the next. Could you say that grades form a spectrum from 0% to 100%? Or in some cases, even more than 100%, huh? You get extra credit. So grades form a spectrum. We use this in a variety of ways, but the most famous one is for the visible spectrum that you see right here, huh? The spectrum of light that we can see with our eyes is the visible spectrum, the range of light. But the visible spectrum is actually only a small part of the electromagnetic spectrum. So let's get straight on this. I kind of wanted to have you learn this last chapter when we studied light, but I thought we should review it. Except now I've lost my marker. There it is. Okay, so right here, from here to here, this is the visible spectrum that we can see with our eyes. And you remember who's the guy's name? It's squeezed in here, not Elmo. That helps you remember all the colors in order. Roy G. Biv fits in here. I can't even write it, so I'm just going to squeeze it down here. Roy G. Biv is in here. This is the visible spectrum, but this is only one part of the entire electromagnetic spectrum. EM for electromagnetic, right? And do you remember we had radio, microwave, infrared, then we go ROYGBIV. After violet, we have ultraviolet, X-rays, and gamma rays. The letter gamma is written, no, that's not a very good gamma, actually. It's kind of like a letter Y in a way, something like that. It's a Greek letter again. Okay? So notice our spectrum that our eyes are sensitive to, the visible spectrum that we can see, is only a tiny fraction of all the different kinds of light that are out there in the world, huh? But it's a range from Roy to Biv, from red to violet, so that's a visible spectrum, isn't it? The whole thing, the electromagnetic spectrum. Make sense? Visible spectrum is just a small fraction of the electromagnetic spectrum. They're both a range of light. One is just a bigger range than the other. Okay, what do you think? This definition for light source, does that make sense to you? Something that produces light? Is that a pretty easy one? So how many light sources are in the room right here? There's a lot. Every light bulb, every computer screen, every phone, right? There's many light sources. What about outside in nature? How many light sources are there? The main light source for us, of course, is the sun. The secondary one at nighttime would be the moon, but then isn't every planet and every star also a light source? Now, does the moon and do the planets make their own light? Or do they just reflect sunlight? Yeah, the moon is like a giant mirror in space, bouncing sunlight back to us. Okay, light source. Hopefully it's obvious. Spectrograph. That was part of our big ideas, right? The big question. How do you use a spectrograph? Well, here's the definition of it. It's a tool. It's a machine. It's a device. It allows us to see and measure spectra from different light sources. Have you ever noticed that some light bulbs are kind of bluish and some light bulbs are more yellowish? Are they emitting the same spectrum? No, they have different spectra, don't they? And a spectrograph would actually allow us to measure that. Okay, now we have three types of spectra, and these are new, so pay special attention. A continuous spectrum. What does this word continuous mean? Forever. There's no interruptions in it, huh? It just flows one thing to the next. So the continuous spectrum is the entire rainbow of light where all the colors have equal brightness. But then we have an emission spectrum. And we looked at this word emit or an emission is when something is released, when something's given off, huh? So an emission spectrum is bright lines that show up against a darker background in a spectrograph. A spectrograph would show us bright lines against a darker background. And this is the result of the light source releasing specific wavelengths of light. It's usually a very hot light source that's emitting light. These wavelengths are brighter than the surrounding spectrum. Now, the opposite of that is what we call an absorption spectrum. These are dark lines on a brighter background. This is because materials absorb specific wavelengths. These wavelengths are darker than the surroundings. It's just like my blue shirt today. What color is it reflecting? What color is it absorbing? It's not absorbing white, it's absorbing red, orange, yellow, green, indigo, and violet. It's reflecting blue to your eye, absorbing everything else, huh? Right? So that's what we mean when we emit something, we release it. It gets to your eye. When it's absorbed, it's held by that thing. So, what I would like you guys to do is to look at these three different spectra. Each of these was measured by a spectrograph. And I want you to label them as either an absorption spectrum, an emission spectrum, or a continuous spectrum. Go back to the definitions if you need help. Which one is an absorption spectrum? Which one's an emission spectrum? Which one is a continuous spectrum? So continuous would have no interruptions in it, correct? Continuous, no interruptions. Emission, it releases light in specific places. Only certain kinds of light are released, just like my shirt is only releasing blue light. Absorption spectrum would hold on to specific colors of light. So again, look at the definitions. Emission spectrum, bright lines against a darker background. Absorption spectrum, just the opposite. Dark lines on a brighter background. And what I want you to notice, do you see that the lines for spectrum B and spectrum C are in the exact same place? You see how those lines match for those two bottom spectra, right? That means it's the same molecule. That means it's the same material. It's like a fingerprint from that material. If it's hot, it's going to create an emission spectrum. If it's cold, it's going to create an absorption spectrum. So these spectra are like fingerprints or barcodes. The spectra can be read just like the barcodes in a grocery store. Reading the spectrum allows us to identify the materials in the light source. Before you learn how to read a spectrum, get your pattern identification skills in shape by matching each barcode in the left with the identical barcode on the right. Just draw lines between the matching barcodes. Dark right back. Dark lines. Absorption. Is that right now? Dark lines on a right background. That be this one? Yeah. What about the emission? Bright lines on a dark background? Now, which one? Yeah. Oh. Let me see what you did. Okay, let's look at these last. Absorption. Dark lines on a bright background. So these is dark lines on a bright background. There you go. That's better, right? So what you did. are you trying to do? Other resolution. Correct. Can I see what you did above? Yeah, let's look at this. What does that say? Absorption is dark lines on a bright background. Which of those is dark lines on a bright background? So, yes, good. See what you did above? See what you did above? Wait till we haven't drawn it because the things we got, they connect to the. It's dark lines on a bright background. Which one is dark lines on a bright background? What you said? So you switch that. Let's see what you did on the upper part there. I got that. You scroll up. Okay. Dark lines on right background? Yes, that's an absorption spectrum. So what's C? Emission. Hey, you guys at home, I don't really have a way to check what you did. So I'll just give you a hint. On this part right here, it looks like everybody's getting letter A correctly, but you better check letters B and C. I'll just point you out to the absorption spectrum, which is dark lines with a bright background. So which of those, A, B, or C, shows dark lines on a bright background? So get that one straight. So you got the correct answers for those three types of spectra. How confident do you guys feel about your identifying the barcodes? Let's see. Give me a dial. You don't feel confident at all. You got it. You're sure you got it right. This is like 50-50. So you're like maybe in here? Okay. I'll check those later. Hopefully we did okay. Let's move on to the next page, shall we? All right, page 6. Okay, so you guys remember we looked at this prism before, right? Yeah, and how it split the light apart? Look up there. And get it just right. You see the kind of rainbow of colors forming there? It's splitting the white light apart, isn't it? Where is it? There it is. Yeah? Hard to get it just in the right place. Sorry, guys. There we go. Splitting the white light into the visible spectrum, huh? So the only thing coming out of this is white light, but white light is a combination of all the colors. So this allows us to split it apart. Oh, what is that? What does that say at the top? What kind of spectrum does your highlighter produce? Let's find out, shall we? Here we go. Prisms and diffraction gratings. Did we look through this thing the other day? This is a diffraction grating. It also split the light apart, didn't it? Yeah? You weren't here to look through this? Okay, well, just look at inside here. You're going to be able to see a spectrum when you look at something that's bright. And that's the only one I have, so you can just pass that one around. You didn't see a diffraction grating before. So we're highlighting as we go, right? Prisms and diffraction gratings are tools that we can use to see spectral patterns. What do I mean by spectral pattern? That would be the arrangement of light in a spectrum, huh? The range of light. As white light passes through the prism, the different wavelengths are refracted different amounts. Refracting it means it is bent. And can you see that the light is coming through here and bending this prism? In fact, a very famous recording, musical recording. Apparently, this is its anniversary. Featured a prism on the cover. And you know Pink Floyd and Dark Side of the Moon. It is the anniversary of that album. Apparently, number 6 of all time in sales. So, by bending the light, by refracting the light, it separates the different colors of light into a continuous spectrum. And that's what we're seeing in this prism diagram. Notice the light wave is bent, isn't it? And the violet light gets bent more than the red light. So it separates out these different colors by their wavelengths. Instrumentation developed by engineers can measure exactly how bright each color is. This is a difficult thing to do with our eyes, huh? It's hard to say, oh, that's brighter than that. But engineers have designed machines that will make these comparisons for us. The instrumentation can assign a number value to the brightness that can be plotted on a graph where position on the x-axis represents color and the y-axis represents brightness or intensity. So let me give you a sample of what this would look like. Let's see. Oops, I want that. So on our axis, we'd have the color, or really we'd have the lambda. What do I mean by lambda? Wavelength. And if we took it down to violet, that would be about 400. And if we took it up to red, that would be just past 800. So this is Roy G. Biv in reverse, isn't it? Biv G. Yor. And over here, we have, I think they said intensity or brightness. Intensity, brightness. How bright it is. So tell me this. In fact, let's go ahead and just fill in Roy G. Biv across the bottom here. What if I had a spectrogram that looked like this? What color would I see? Well, look at Roy G. Biv. What the pink is lined up over the yellow, isn't it? Does that make sense? On the other hand, what if I had indigo and orange were both released by that light source, weren't they? Does that make sense? It'd be indigo and orange being both released equally. Now, what if I had that? A lot of violet and a little green is being released by that light source. So this is how you can read a spectrograph, right? You can see what color it is, what wavelength it is, and you can see how bright it is. There's actually 2 S's in brightness, huh? Right? And we can make those comparisons. Oh, what about this one? How about that one? Every color except, yeah, it's kind of a blue-green that's missing, isn't it? Does that make sense? How you could also look at a reverse spectrum like this? Okay? Okay. I'm down here now. Hopefully you're highlighting as we go. Light passing through a cool gas. I'm not talking about some gas source that's got, they're just so cool because they wear the right clothes and they hang out with the right people. I'm talking about low temperature gas, correct? Light passing through a low temperature gas will produce what is called an absorption pattern. when seen through a diffraction grating or through a prism. And dark lines will appear in the continuous spectrum. The dark lines are actually created by the gas absorbing the energy of the light. That's what makes that absorption spectrum. We can identify the gas based on the distinctive pattern of lines that appear in the absorption spectrum. It's just like fingerprints. This material, these elements in a gas, will absorb these wavelengths, but not those wavelengths. They each have their own pattern. Conversely, an emission spectrum is seen as bright lines against a dark background, and it is produced by hot gases emitting photons. What's a photon? Particle of light. Particle of light moving through space in a wave. The higher the frequency, the more energy in that photon, right? Or it might have really cool wavelength, just chill, relaxed. Conversely, an emission spectrum is seen as bright lines against a dark background. It is produced by a hot gas emitting photons. Again, the pattern the gas creates is dependent on the type of gas. A particular hot gas shows emission lines in the same exact places that the same cool gas shows absorption lines. So look up here. If we go back to this diagram, didn't we have emission lines and absorption lines in the same place? In fact, I don't know if you can tell on your screen, but even this one lines up. There is a blue absorption line right here, an indigo absorption line, and there's one too. The exact same pattern, but one is the negative of the other, huh? One is glowing, releasing light. This must be a hot gas. And that same gas, when it cools off, absorbs the same kind of light. You okay with that? The exact same pattern, regardless if it's an emission or an absorption spectrum. The pattern does not change, but whether you see an absorption or an emission pattern through the diffraction grating depends on whether the gas is hot or cool. The resulting spectrum will have a characteristic pattern of light and dark that, when analyzed, reveals the composition of the light source. Yes, sir. Yeah, just let me show you what you're going to do next so you know. Or did you already figure it out? Okay, so we go down to, here are, go ahead, Sawyer. What do we have? About half a dozen different spectra. Are these emission or absorption spectra? Yeah, these are absorption spectra. Do you see the top one is an unknown gas? And then we have 5 gases: helium, oxygen, neon, argon, and xenon. 5 different gases. We know that these are their their absorption spectra. You have to match the unknown to the correct known gas. And there are 3 questions for you to answer on the side. Okay, so I think when you name that unknown gas, that's question 3. So you've got 3 questions to answer there about these spectra. What do you think? Does it show dark lines? It shows dark lines against a bright background, as if something's been taken away because it's been absorbed. If it's an emission spectrum, it would be bright lines that are being released. So yeah, these are appearing to be the ones that it's got a B and a P in it. ABSORPTION. A hot gas is going to emit lines. It's going to emit energy if it's hot. Does that make sense? That something hot would kind of be glowing. In other words, emitting energy. So something hot is going to, think of it as glowing. It's releasing light. It's emitting energy of specific wavelengths. And so that's when we get an emission spectrum if it's hot. On the other hand, if it's cool, it's going to absorb energy. As the light passes through it from behind, it's going to absorb some of that energy. How are we doing at home? Give me a thumbs up when you're done with those 3 questions. How are we doing in here? You guys ready to move on? What does that mean? So to help us figure out what's going on with this discussion of the emission and the absorption spectrum, the hot gas and the cool gas, I've just looked for this photograph of an object in space that you could see tonight. If you looked in the right part of the sky with a big enough telescope, you would see this guy, the Orion Nebula. Okay? A nebula is a huge gas cloud in space. It's made of different gases and dust. And it is not glowing by itself. It just happens to be reflecting some of the light from stars around it. That's what allows us to see it. So these stars, like, let's look at this star right here. Can you see that one that I circled? That star is actually between us and the nebula. It's closer to us than the nebula is. If it was behind it, its light would be blocked off by the nebula. That's why we can see it, because it's in front of the nebula. Does that make sense? So when it talks about a nebula, this is what we're referring to. So let's just do this. Here's some gas cloud. Here's a nebula in space. And here is a star. The star is also gases, but they're superheated, aren't they? To the point that they're releasing light, they're emitting light, correct? And let's say that this star is releasing mostly red light. How does that sound? Yeah? Now, if we could look directly at that star, our emission spectrum would look like this. This is Roy G. Biv, isn't it? Does that make sense? We'd see the red light. But when the light gets to the nebula actually absorbs most of those colors. And as a result, the nebula is going to have a different spectrum. It's going to have a spectrum that looks more like this. Does that make sense? Because it's made of a different molecule, it's going to have a different spectrum, and it's going to be an absorption spectrum. This one's one bright line, isn't it? This one is all bright, but with a dark line. Does that make sense? In fact, I could fill it in like this, couldn't I? It's got this whole dark line here. Whereas this one has just the bright line on the dark background. Picked up my hand as well as my pen. So this should all be filled in. Here's my spectrum. This one, on the other hand, would have red, orange, yellow, green, and then it would have this black zone here with nothing, huh? And then the violet. So this would be an absorption spectrum. This would be an emission spectrum coming from the star, an absorption spectrum coming from the nebula. I'm going to wait for Leo. All right, that finishes page 6, and that actually finishes the little assignment within the big project. It's made of multiple assignments, right? That finishes the assignment called Spectral Fingerprints, and we're ready to start on graphing the rainbow. So move on to page 7. And once again, we're going to start with some reading and highlighting. Recall that when light from any source, a light bulb, a computer monitor, or a planet, when that light passes through a prism or a diffraction grating, it produces a unique rainbow pattern, a spectrum. The pattern may be mostly dark with a few bright stripes, which would be an emission spectrum from a hot object, or it could be mostly bright with a few dark stripes. And that would be an absorption spectrum from a cool object. The intensity of the light at each wavelength can be plotted on a graph once it's been measured by a spectrograph, which is shown in this graph right here, isn't it? It's got the color along the x-axis, and it's got the intensity on the y-axis, the brightness. Which two colors would show up most in an emission spectrum from the light source shown in this graph? Please answer the question. Go ahead, write down your answers. Okay, next, compare the spectra below to their intensity graphs. Notice that the brightness or dimness, which is the intensity of the spectra, these are shown by the graph, with the line on the graph rising and falling. Label each spectrum graph pair. So this spectrum does go with this graph. These aren't mixed now. They're side by side. Label each pair as either an absorption spectrum, a continuous spectrum, or an emission spectrum, and explain why you chose that. So the type of spectrum, you write down the name of the spectrum, and then the reason, why did you decide that was that type of spectrum? It's emitting that specific color, right? So it only releases certain colors, correct? Okay, let's look at a couple of details here. So here in this spectrum, it looks like every color is shown about equally. Oh, and the graph definitely shows that, doesn't it? It's just a flat line showing that every color is shown at an equal amount. Look at the next one. it's almost completely dark except for that kind of yellow and green zone, isn't it? And when I look at the graph next to it, I see that it's a flat line on the bottom, and then it rises up in the middle, right where the green and yellow are shown, huh? So it goes from no light to lots of light, and then back to none, huh? Meanwhile, the bottom graph is almost an entire spectrum, but it has two big zones missing in the red and the orange colors, huh? When I look at the graph, I see that the light starts out and immediately drops down to nothing, huh? It goes back up, but then drops down a second time. And then it goes up and shows the rest of the spectrum again. Does that make sense how you look at these? So these are simplified versions of what these spectra can look like. Now, a scientist might not actually even look at the different colors. Instead, they only look at the graph because it's going to actually measure the differences between the intensity of different colors, their brightnesses, more accurately than we can judge with our eyes alone. So let's move on to page 8. And all you have to do here is, once again, match the spectrum to the graph. So notice for the first graph, I see a bunch of spikes. I see 6 spikes coming up from the bottom, huh? So if it's high, we should see light there. On the other hand, on the second graph, I also see 6 spikes, but this time they're going down, aren't they? So this is where it would get dark, where it goes down. If it's down towards the bottom of the axis, it's dark. If it's towards the top of the axis, it's bright. No, all you do is just draw lines to match the spectrum with the graph. Does that make sense? So you're just going to connect them with lines. I don't know. I'm just going to do this. Whoops, I didn't. Oh, you make them to the. Oh. Yeah, you just kind of random. I'm going to do this randomly because I don't know which one's which. But this is all you have to do, right? Yeah, just show me which is which. And I didn't really give you an answer because I didn't pay attention to which one I was connecting. But just show which graph goes with which spectrum. Remember, if it's dark lines, that means there's no light coming through there, correct? And the graph would drop down where there's a dark line. If it's bright lines, the graph would rise up where it's bright. Personally, I think our first spectrum might be the hardest one to do. Going down, right? If it's a bright line, like this one is bright lines on a dark background, so that one's going to have to spike up, right? It's dark lines on a bright background. If it's dark lines on a bright background, it's going to spike downward. And they might spike down different amounts, huh? So this would be absorption, and this would be emission. How are we doing on this, you guys? Let me just do a couple with you and see if you agree with what I thought. So I noticed that this one here had 3 lines close together and then 3 lines far apart. But I also noticed that this one here was particularly wide, huh? That one was a pretty big gap. So it might not look like a spike. It might come down and go across before it goes up again. So I looked for one like that, and the one that I found to match it was down here. Does that make sense how I chose that one? It's got 3 close together. Then it's got 3 far apart, but the middle one of those 3 is very broad. So I chose that one. Let's look at another one here. This one is pretty interesting too, because did you notice the way that it isn't just flat across the bottom, like the others are pretty flat across the bottom, but this one has that little rise here. So that means all across the middle, there's going to be some dim light. It's not going to be completely dark. This one's going to have dim light all the way across the middle, but it should have a couple of really bright zones next to that dim light. And then maybe one other little brighter, but not too bright. Find something to match that one. It's, for most of the spectrum is visible. You can see most of the spectrum, but it's dim. But then there's a couple brighter spots on it too. I would agree. I don't know how to do that. You do Control Z. Didn't you turn something sideways on the last project? No, you turned the front page sideways. No, I downloaded it. I downloaded the front page like that. Yeah, I couldn't make that, but I could fix it. You know how to fix it? Yeah, that's my entire thing. Run like the we have very lot of changes. It's gone from portrait to landscape. It's the entire document. Control. I don't know if it's called control. That's what was working on. Did you? No, I was just like typing. Probably. Because he's a freshman. Not a freshman. Oh, I found something. Here you go. I got it. You got it? What did you do? Shift Control and then either plus or minus. Shift Control and either plus or minus. Look, it's very on my computer. It's fairly well. Make sure it's the whole thing. Whoa, it's not bad. All right. Hopefully we're done with page 8 now. Yeah. Let's move on to page 9. Wait. Hopefully we're done with page 8, page 9. Okay. So we're going to make a graph ourselves now. And there's one thing that's kind of tricky about this graph. It's called a log graph, or in this case, a semi-log graph, which means it uses a logarithm. I don't know if you've used logarithms in math or not. You don't have to really worry about it too much. It's kind of the opposite of an exponent. When you go x squared, that's the exponent. Logarithms are kind of the opposite of that. But first of all, let's read through the intro and highlight the important stuff. We're going to plot a spectrograph for Earth's atmosphere. In order to plot a spectrograph of Earth's atmosphere, we have to use a special type of graph called a semi-logarithmic graph. Instead of increasing evenly across the x-axis, every section of the graph increases by another power of 10. So look at this little sample down here. You see where it has 10, and then there's 10 lines. So it would go 10, 20, 30, 40, 50, 60, 70, 80, 90, and now it's at 100, which is 10 squared, huh? But now we don't count 110, 120. Now we're counting by hundreds. So this is 100, 200, 300, 400, 500, 6, 7, 8, 9. That takes us to 10 cubed, which is 1,000, huh? But that means we're now counting by thousands. 2,000, 3,000, 4,000. Does that make sense? So we change our count all along the way as we go. With me on this? We change the way that we count. Use the data provided about the wavelengths of different molecules in Earth's atmosphere to draw a spectrograph. Just make a spike for each molecule at the correct wavelength, showing its abundance. So how many spikes will we have in our graph? We're going to have 4 spikes, one for nitrogen, one for oxygen, one for water vapor, one for CO2. Which will be the biggest spike? Nitrogen, because it makes up the biggest percent of our atmosphere, right? 78% of the atmosphere is nitrogen. So where do we put that nitrogen spike? Oh, at the 3 nanometer mark, right? So look on the bottom. Where do we find 3? That's because it's this logarithmic graph. So they get squeezed closer and closer together. If you were to take the logarithm, which is a whole mathematical function, you would find out that it looks like this. What this allows us to do is go from a really small number, from 1, to a really big number. This is 1 million up here. 10 to the 6th is 1 million. We went from 1 to 1 million on here by using this special paper. Does it kind of distort the graph? Yeah, it does. But it also allows us to see this huge range. So where would we find 3 nanometers on here? Here's 1. Here's 10. Where must 3 be? Don't you think it must be right there? And how high are we going to make this spike again? At 78, yeah. So you're going to make a spike up to 78 on the 3 nanometer mark, huh? It's like right there. I'm just going to put a point there for now. And I'll draw my line in a minute. What's the next one? 20%, that's the easy part, isn't it? What is my nanometers? 150. So now I have to go down here. Where is 150 on this graph? Where's 100? Well, here's 1. Here's 10. What's 10 squared? That's 100, isn't it? What's 10 cubed? 100 times 10 makes 1,000. So 150 has to be in here somewhere, huh? So remember the way this goes. Watch as I'm drawing on here. This is 100, 200, 300, 400, 500, 600, 700, 800, 900, and then we get to 1,000, huh? So where's 150 on there? This was 100. Why it's not allowing me to write on that? this was 200. Right? Let's undo all this. I would suggest this is not the best time because this is tricky. If you understand how to do this graph, that's one thing. You did it? Okay. Here's 100. Here's 200. So where's 150? Halfway between those two, huh? So then you're going to draw a line at 0 and have it spike up to wherever you had to go. Does that make sense? So the 150 went up to 20, didn't it? So I'm going to spike up to 20 right there.
Would we connect it all?
Yeah, that's what I was just doing. I was connecting. But making it look like a spectrograph means you connect it with a flat line here, and then you spike up. And then back down to 0 again, right? It looks something like this. Right? Yeah. So you end up with a single line, and it's going to have across the bottom, and it's going to have 4 spikes of different sizes. 2 really small ones, I think, huh?
No.
I like that idea. Yeah, let's label each spike with its name of the molecule. Very much for suggesting that. That's such a good idea. I think you get bonus points.
I get bonus. I wanted to say.
And you guys at home, it doesn't say it on there, but I want you to label the graph with the molecule. So this first spike that I drew on here, I should label as, which molecule was that? Takes up 78% of our atmosphere? Nitrogen. So label each spike with the correct molecule, okay? And then I want to vote with what we're going to do with the last almost 20 minutes of class here. So we have 2 choices. One, we move on and get more of this done, pages 10 and 11. We might only get through 10 and then you'd have to do 11. Or do you guys need extra time to finish page 4? You might have finished page 4 already. You might not have. I don't know. What do you guys think at home? Do you need more time for page 4 or should we keep going? So you guys want to do page 4. Any other votes?
Lava. 10. Just look like that.
Okay, so, I just want you to get, what do we have? You should get all 9 pages finished in the next few minutes, okay? If you didn't finish page 4 on your own, you've got some time to do that. This graph was page 9, so get that finished up. And that'll do it for today.